if it's discrete, and G mod gamma has a finite G invariant measure. So for short, I will write that mu of G mod gamma is less than infinity, where mu here is the Haar measure on G descending to the quotient. So this number here will be called the co-volume of gamma. And the question that I'll consider today is, given a group G, what is the set of co-volumes of lattices in G? So something I forgot to say, distraction about the microphone. So there are two kinds of lattices. A lattice is uniform or co-compact if G mod gamma is compact. So for example, the integer lattice Zn inside Rn is a co-compact lattice because the quotient is just the torus, and otherwise it's non-uniform or non-co-compact. So I'll just generally write non-co-compact. We're losing the chalk. So an example here is, which we've already seen today, is SLNZ inside SLNR. So the quotient here has finite volume, but it is not compact. I'm going to consider three classes of groups today. Our results are about the third class, but in order to put them in context, I'll first talk about the case where G is SL2K, where K is some local field. Then I will talk about where G is the automorphism group of a tree. So this is also a locally compact group, as I'll explain. And then the third case is where our results lie. So this is where G is a Kac-Moody group. And I'm not going to assume that you know what these are, so I will tell you later on. The reason I'm putting it in the middle is because these groups do have some algebraic structure similar to SL2K, but they're not linear. So I'll just emphasize that. So a lot of the things you might do very easily in this setting, you have to work a lot harder here. And what we ended up doing is using some techniques from geometric group theory, from groups acting on trees, in order to understand this case as well. So that's why I'm putting it in between. Okay. So the first case, so the kinds of fields we're talking about are the reals or the complexes or some non-Archimedean fields, the p-adics or Laurent polynomials over the finite field. And a well-known result from the late 40s for this case, so a theorem of Siegel, is that if I have any lattice in SL2R, its co-volume, so let's call that G, is bounded below by pi over 21, and this minimum is actually realized by a co-compact lattice, which is unique up to conjugacy in G. And that lattice is the 237 triangle group. So you start with a hyperbolic triangle with vertex angles pi over 2, pi over 3, pi over 7. Look at the group generated by reflections in the sides of that triangle, and the lattice of minimal volume will be an index 2 subgroup of that. Question? Okay, So this is the usual Haar measure in SL2R compatible with the action on the upper half plane. So the volume here is the area of the fundamental domain in the upper half plane. So for example, if gamma was SL2Z, then this is its fundamental domain, and the coat volume will be the area of this triangle. So we have a hyperbolic triangle with vertex angles 0, pi over 3, pi over 3. So that's area pi over 3. So the standard normalization. Yeah. I'm following Lubotsky. So he cites, his paper, which I'll get to in a moment, is called a non-Archimedean analog of Siegel's theorem. So take it up with him. Okay. So what else could we consider? So without listing lots of results, I'll just point out that lattices in SL2C correspond to hyperbolic, well, in general, hyperbolic 3 orbifolds, or if they're torsion-free, hyperbolic 3 manifolds. So there's been a lot of study of, for example, what's the hyperbolic 3 manifold of minimal volume, what's the co-compact one of minimal volume, what's the volume spectrum, that sort of thing. But it would take me too long to list results here. Now, in this setting, it's a work of Lubotsky and Weigel. So they found the lattice of minimal co-volume in SL2K, where K is a non-Archimedean local field. So a complete list is this, finite extensions of this, which is the main content of the second paper, and Laurent series over a finite field. So this is characteristic 0, and this is positive characteristic. A surprise in this paper was that in the case SL2 Laurent series over a finite field, the lattice of minimal volume is this group. It's called a negative parabolic subgroup, for those who care. And in fact, this is non-uniform. It's a non-co-compact lattice. So it's a contrast with the result that Siegel got in the real case. Now, this group is the first example of the Cass-Moody groups that we're talking about. So I emphasize not linear here. Obviously, this is a linear group, but it's the only example which is linear. Something I'll use later on is that all of the groups that they consider, let me just write it out this way. This is the case I care about. Okay, this has a tree associated to it, called its Brouhard-Tietz tree. And this is Q plus 1 regular. So the way that SL2 of Laurent series over a finite field acts on this tree is somewhat analogous to the way SL2R acts on the upper half plane. It's a highly transitive action. The stabilizers of points are maximal compacts. The action is by isometries, and you use this action to understand the group. This lattice, gamma 0, inside the tree has fundamental domain, just a ray. And this fact here is, and the fact that this is a lattice is called Nagal's theorem. It dates from the 1950s. So what they did is show that this is the lattice of minimal volume. Safidi has actually done some recent work on Chevrolet groups in higher rank. And in that setting, he's also shown that the lattice of minimal volume is not co-compact. So maybe this is a sort of low-rank phenomenon, perhaps. So my second setting is lattices in automorphism groups of trees. So I'll call this tree lattices. So T here is a locally finite tree. So by this I mean a simplicial tree so that there are finitely many edges glued around each vertex. And G is the group of automorphisms of T. Now, this is with the compact open topology. And under this topology, this is a locally compact topological group. So to give you some idea of the topology here, a sequence of elements going to the identity is a sequence of elements which fix larger and larger balls in the tree. So for example, if you had a 3 regular tree, 3 edges glued around each vertex, you can get a sequence of elements which fix larger and larger balls in the tree, but are not the identity. Maybe they just flip 2 edges further and further out. So you get a sequence going to the identity which is not constant. This is a non-discrete group. It's work of Bass and Kulkarni determining exactly when the automorphism group of the tree is non-discrete. But you can think about a 3 regular tree or an M regular tree where M is at least 3. Okay, now what does a lattice look like in this setting? Over here, these lattices are arithmetic groups. Well, a lattice is discrete. So in this topology, discrete just means that it acts with finite stabilizers. So the group stabilizing a vertex or the group stabilizing an edge is finite. Okay, so that's fairly easy to recognize. What's a lattice then? So we need the quotient to have finite volume, and we can use a normalization of the Haar measure which is due to Serre. So he showed that for any discrete subgroup gamma in G, we can normalize the Haar measure so the co-volume is given by a series. We're going to sum over the vertices of some fundamental domain, and we'll sum 1 over the order of the stabilizer of that vertex in gamma. So gamma is discrete, so this is a finite group here. We have 1 over the order of the stabilizer. Now, if gamma was acting freely, what this would be doing is just counting the number of vertices in the fundamental domain. But if gamma is acting with torsion, what this is doing is weighting each vertex by 1 over the order of its stabilizer. So if you may be familiar with Euler characteristic, this is the same sort of calculation to get this. So this may or may not converge. It converges exactly when gamma is a lattice. Okay, so this could be some. Pick one. Yeah. Well. Okay, it depends what you mean by fundamental domain, I guess. So, yeah, strict fundamental domain, this is fine. Okay, so, right, so there's been a lot of work on tree lattices, so I'll just tell you 2 results which contrast this. In general, the situation is very flexible. There's a lot of wild behavior. So one of the first results which drew attention was due to Bass and Kulkarni. About 90. So they constructed what are called towers of lattices. So a tower of lattices is an infinite, strictly ascending sequence. So often in group theory, you fix a group and you're looking at sequences of groups going down. This is going the opposite direction. These groups are getting bigger. And what the consequence is, Well, if you look at the co-volumes, so we go up here with index 17. That means you divide the co-volume by 17. So each time you go up here, you're dividing the co-volume by some positive integer. So you get a sequence of lattices with co-volumes going to 0. Whereas in Siegel's theorem, which I've erased, this one, there is a lower bound on the volume of lattices, and that lower bound is actually achieved. So they constructed towers of co-compact tree lattices. Carboni has constructed towers of non-co-compact tree lattices. But for co-volumes, another result, this time due to Bass and Lubotsky, who wrote a book about tree lattices. So T is the M regular tree, where M is at least 3, then for every positive real number, there's a lattice, so a non-co-compact lattice, in G, the automorphism group of tree. Let's give it a name, so call it gamma R, with co-volume exactly R. So every positive real number is the co-volume of some lattice. Moreover, the quotient is the same quotient as the Nagel lattice. Okay. So even fixing the quotient, you can get every positive real number as the co-volume of some lattice. The way this works is they put direct products of cyclic groups on each vertex, and you do a clever argument with matrices, and they increase for a while, they decrease, they increase, they decrease, and you can get convergence to R here. Okay. So now I'll talk about Kac-Moody groups. Okay, now I'm going to do some background on these groups. To save time, I'll say that everything I'm saying is from either one of several papers of Remy or a paper of Remy and Ronan, or a paper of Capras and Remy. And if you want to know precise attributions, I can tell you afterwards. Now, when people say Kac-Moody group, they could mean one of two different kinds of groups, and I'll use two boards to go through this. Talking about what is sometimes called minimal or incomplete Kac-Moody groups. And they could be talking about what is sometimes called topological or complete Kac-Moody groups. So I'll call these ones lambda and these ones G. So our results are going to be about lattices in these groups. An example would be the arithmetic group, say SL, let's do SL2. And an example here, which I've already mentioned, is now, these groups can often be thought of as generalizations of arithmetic groups. I'll say a bit more about their structure in a moment. These groups can often be thought of as generalizations of algebraic groups. They're obtained by completing the minimal or incomplete group with respect to some topology that I'm not going to tell you about. But it comes from a group action on a tree, and I can tell you the details. So you start with this group, you complete it, and you get this group. And the original group embeds in the completion. Yes? Yeah, just T inverse. So, yeah. So we could have completed with a T or with a T inverse. There's actually positive and negative completions. Because I use T inverse in my notes, I don't want to have to switch everything around, but you can if you want to. Yeah. So in general, there will actually be two completions. I'm just going to pick one of them and go with that. Okay. So a little bit about the structure of these. Okay, so I'll start here. Kac-Moody groups came after Kac-Moody algebras. Kac-Moody Lie algebras are infinite dimensional Lie algebras, defined by Kac-Moody. And a natural question once we had these algebras was, is there a Lie group-like object associated to them? So some sort of infinite dimensional Lie group. Tietz constructed a functor from Kac-Moody algebras over any field to Kac-Moody groups over any field. This is over, so everything I'm saying is we're doing over finite fields, but a lot of what I'll say on these boards will be true over any field. These groups have a presentation which generalizes the Steinberg presentation of Chevalley groups. So they have a lot of the same structures as finite groups of Lie type, even though they're infinite groups. So what is this structure? Well, for example, they have an important subgroup called the standard Farrell subgroup. So I'll write that as B. And the completion of that is called the standard Iwahori subgroup, B hat. So I'll write hats for completions. I'll say what this is more precisely in a moment. So following this example, we have also standard parabolic subgroups. P1 and P2, and the standard Farrell is the intersection of them. So P1 is, for example, this group here. And then P2 is take the elements of this and modify slightly. And, okay, so we take the word parabolic and we blend it with the word Iwahori, and we get what are called parahorics. So, for example, P1 hat, I'll do it T inverse. Okay. Now, once we have these groups, we can build a tree out of them. Okay, this is how the tree, the Brouwer-Tietz tree for this is constructed. So call the tree X. Its vertices have one of two types. They're the cosets of P1 in lambda and the cosets of P2 in lambda. And then the edges are the cosets of B in lambda. And the way these are glued together is just the natural way by cosets. So you can glue edges to vertices like this. It's a theorem that you actually get a tree. And the group lambda acts naturally on the left on this with quotient and edge. Over here, it's a theorem that the completed tree is the same as the original tree. So its vertices are the cosets of the parahoric subgroups, and its edges are the cosets of the Iwahori subgroup. So we have a group acting on a tree in exactly the same way. Okay, the kernel of the action is the center of lambda, which is a finite group, and it's a quotient of the direct product of two copies of the multiplicative group over this field, so it can't be terribly complicated. Over here, the kernel of the G action on X is also its center, which is the same as the center of lambda. Now, one other thing we'll be using, these groups have very nice decompositions, which are called Levi decompositions. So PI splits as Li semi-direct with Ui. Li is a finite group. Okay, so T is what's called the torus of lambda, and it's, let me just say that it contains the center and it's a finite group again. And then Mi is either SL2Q or GL2Q. So the upshot is that Li is a finite group that we understand pretty well. We have a good idea of what its subgroups are. And then Ui is an elementary abelian P group. So every element is of order P. It's just lots of copies of cyclic group of order P. The Levi decomposition occurs over here too. So we have is the same Li, so that same finite group, and now the Ui hat is an abelian pro-P group. Okay, so now let me tell you our results. Okay, so I will save a whole lot of words which I've tried to explain here a little bit. So we have G is a complete, so it's the completion of a minimal one. Complete, rank 2, I'll explain more in a moment. Kac-Moody group. Over the finite field, FQ, where Q is the power of the prime P. With symmetric, okay, so Lie groups have Cartan matrices, Kac-Moody groups have something called a generalized Cartan matrix. So generalized Cartan matrix okay, what the rank 2 is about is if M is bigger than 2, this is actually a rank 2 matrix in the usual linear algebra sense. So this is not positive definite. How does this fit into this example here? So when M equals 2, an example of such a group is the example over there. And for short, I'll just refer to this as the affine case. This is a linear group. In general, these are not linear groups. Okay, so complete blah, 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 blah. Our theorem is only about symmetric generalized Cartan matrix. You could also have a -1 here and an integer bigger than 2 here. What goes wrong, or what doesn't go wrong, what makes life harder is that these UIs are no longer abelian groups. So that's something which in future we might consider, but at the moment we're just doing the symmetric case. Okay, so what do we prove? then, so we find a lower bound on covolumes of lattices in G. Okay, so this is 2 over Q plus 1, Q minus 1. And this is the order of the torus, so this is this little finite group inside G. We can have different orders depending on the case. This minimum is achieved by a non-co-compact lattice, so as in Lebotsky's theorem. And its quotient is the same kind of quotient as in Nagau's theorem. So so it's the analogous lattice to the one that Lebotsky shows as the lattice of minimal volume. Okay, we can also say something about co-compact lattices of smallest volume. Here we had to throw out some small values of Q because there are some SL2Q has some weird subgroups for small values of Q, and we needed to avoid those. So for Q at least 600, the minimum co-volume among co-compact lattices is, so 2, okay, this is the center of the group, also a little finite group, delta is 1, 2, or 4, depending upon the case. So you will notice, so the center's inside the torus, so unless Q equals 2, this is definitely bigger than that. But this result is for all values of Q. There's a sort of easy argument to say the minimum has to be non-co-compact. So remaining... Yes, yeah, thank you. fixes a ray from somewhere on this axis up to epsilon, and then it acts, it's a pro-P group, and the finite order elements act inside this black P. So it's fixing up here, it's actually fixing the entire horrible based at that point on the boundary, and then around the outside of the horrible, it's actually a pro-P group. So it can, it's not the same group as those you guys I was talking about earlier, but they're making composition, it's still about the same. Okay, so a finite each element of U fixes that, in fact it fixes the entire horrible. Let me just draw the case D equals 2, equals Q, so at each level outside the horrible, it's either switching all of the edges on that level, or it's fixing all of the edges on that level. Okay, so it's some big rectangle action. So those are the three ingredients we showed at the end of the stabilizer. In the outcome case, you identify the boundary with the projected line over this field. And then the stabilizer of, say, the end point on the boundary 1, 0 is the matrices which are arbitrary. Okay. Then U will be the part 1, 0. With ones on the diagonal, and then MR is the diagonal part of this. And the translation G will be so they have this decomposition of an end. What we include is that this is actually semi-direct relation. So we have semi-direct decomposition, which is obvious in the outline case. So this is a normal subgroup of this, normalized with the diagonal matrices. And all the P elements in this N stabilizer are with U. Now, why is this important? So we have a proposition which takes a geometric argument to prove that a P element in G fixes an end. It's an argument by contradiction. So any P element in G fixes an end. So actually that says that the P elements in G are precisely inside here. Now why do we care about P elements? Well, in the affine case, elements of order P are exactly the same thing as unipotent elements. And understanding covolumes and understanding lattices in general is very important to understand the unipotents. So for us, it was very important to understand the elements of order P. Using these results, we're able to show that co-compact lattices don't contain any elements of order P, and then this is also the starting point for analysing how the non-co-compact lattices act in the tree. We know that they have to fix at least one end, and then you get an analysis in terms of parabolas and what the function looks like from there. So, I'll stop. Yes. Is not a general area. It would be a area if the characteristic field is not by n. So, yeah.
Then, now, when you have two things, you have two points. So if you take One,
So the tree is not necessarily regular, it's not a symmetric case. And in terms of the group theory, that translates to this group not being there. We'll certainly use that. So if we get more, we're trying to think about how if we get more of that, that would be symmetric.
yeah, constraints.
Yeah. Yes.
In the James Curvature matrix that you get the different lattices as the subgroups of monomorphisms with full monomorphisms of three.
Yeah. Yeah, so it's the same low. I mean, but in that lower band, there's the order of the centre of the group, for instance. Sorry, the order of the torus.